Hello and welcome to another let's do algebra and stuff online. That was the worst introduction I've done in a long time. I hope you appreciate that. Today we're going to be talking about, come on, my pen's not working. Ooh, might have to pause here. Okay, hold on a second, guys. I apologize. I had to change the battery in my pen. It had died. Here we go. So today we're going to be doing 7.2, which is all about dealing with rational exponents. So we did do a little bit of exponent work yesterday because we had looked at what would happen when my roots and my exponents interact when they were the same powers. We were doing stuff like, ooh, what happens to square roots of squares? And we saw that that came out as an absolute value. And like even roots, sorry, odd roots, like didn't do that. It just came out the same. Yay! So what we're going to look at today is like what if I have some other stuff interacting or going on? So let me give you like a little bit of a motivator. So suppose you have a triangle. No, that's not going to work because it only wants to do a rectangle. Sorry about that. Do 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 do. And it happens to be a right triangle, and you know that one of the sides is 4 and the other side is 3, and you're like, I don't know what this side is. It could be anything. Just kidding. It's not that it could be anything, it might be something different. I don't know. Let's find out. So, if you remember back from algebra, you had this rule that if I looked at a right triangle, the squares of the sides added together would match the square of the hypotenuse. This was known as the Pythagorean theorem. So for us, that tells us that 3 squared plus 4 squared, because that's my a and my b, except for I put them in opposite places. For I put my 3 and my 4 in the wrong spot. A was 4, b was 3, and I square them, I should get c squared. And you're like, okay, that's 16, that's 9, and when I add those together I get 25, c squared, and you're like, oh, what when I square it will give me 25? Or this is the same as saying, well, c is going to be the square root of 25, which is just 5. And that's kind of fun. Um, and that works good because, well, we know what when I square it will be 25, it's 5. But what if we had something else? What if our triangle was different? What if our A was 5 and our B was 2? I tried to draw my B a little shorter this time, but I didn't succeed all that well. And I was still trying to find C. So in that one, you'd have 5 squared plus 2 squared is C squared. And you're like, ooh, 5 squared, we just did that one, that's 25. And C squared is 4, or sorry, 2 squared is 4, and that's equal to C squared. And you're like, ooh, that's 29 equals C squared. Uh-oh. I don't know a perfect square that'll do that. So C is going to be the square root of 29. And then we had to turn to a calculator because we couldn't do that any other way. And we had to estimate it, and I'm going to round a little bit and call it 5.39. And this can happen to you. You might not get a perfect solution to this. So what we're going to look at a little bit today is interacting some things with each other and getting some values that, might not be perfect, but that's okay. So in order to do that, I'm going to remind you of some stuff you hopefully remember but maybe have forgotten from exponent rules. And if you forgot them, that's okay. That's why we're doing them again right now. So you may remember that if I have something to a power, that's supposed to be an n, and then to another power, you can just multiply those two powers together. So this was like if I have 4 squared and then I cube it, that's going to be the same as 4 to the 6. You multiply them, you don't add them. If I have two things inside some parentheses to a power, I can just do them individually. And that's just like if I have 2x cubed, I can actually do 2 cubed times x cubed, which would give me 8x. And then if I have, oop, I didn't need parentheses that time, sorry about that. If I have two things that have the same base to two different powers, I can just add their powers. It's supposed to be an n plus an n. This was like what would happen when we have x squared times x cubed, and we'd be like, oh, they're both base x, so I'll add their powers together. How many powers of x do I have? I really have 5 powers of x. So remember, x squared is just x times x. X to the fifth is x times x times x. How many x's do you have multiplied there? Well, really, I have 5. And then, oh boy, we're almost done, I promise. Oh, this is not going to fit all on one page. It's unfortunate. Let's scroll this up just a little to make it fit. Make it fancy. Okay, so then if I have a negative exponent, that, of course, we might remember is the same as doing the same thing but in the denominator. So my exponent becomes positive. This was like when we had things like 4 to the negative 2. What we would do is we'd say, oh, that's really 1 over 4 squared, which is the same as, well, when I square 4, I get 16. So we could actually calculate that. And then last but not leastly, if I have two things with the same base being divided by each other, that's the same as subtracting their exponents. This would be like when I would look at 4, why do I keep using 4? To the third over 4 squared. What you would do instead is 4 to the 3 minus 2, which would be just 4 to the first power, which is the same as 4. Beautimous. Now I'm going to use that idea to come up with how I can do exponents of things that aren't necessarily whole numbers, as weird as that seems. So since the beginning title of this is rational exponents, we're going to look at ratios of exponents. And we're going to do that right now. So non-whole number exponents. And I'm going to motivate this using roots. So let's think. So suppose I've got like the square root of 4 times the square root of 4. Yeah? I'm actually going to look at another way that you could write this. So you could just do this as, okay, I got 4, I'll do the square root, that'll give me 2. I've got 4, I'm doing the square root of that, that'll give me 2. That ends up being 2 times 2, which is 4. And hopefully you recognize, oh, this is the same as multiplying something by itself. So this is like the square root of 4 squared, isn't it? Interesting. Okay, so hopefully you see the connection here that if I square a square root, I get what was inside that square root back to each other. Not too much of a shocker there. Cool. So now what I'm going to introduce to you is the other way we could write this. And that's using what are called rational exponents. Rational exponents are if I have something under, I don't want to use 4, sorry, I meant to use like A or B. So if I have a number under a specific root, that is the same as having that base value to the fractional version of that exponent. And let me show you how that works and why it works, because otherwise that seems like a crazy idea. And the answer is, it's all in the roots, man. And the shit. Okay. And the answer to that is, it's all in the roots. Man, that sounded unnatural. Okay, so suppose I'm looking at 2 square roots of 4 again. So back to our previous example that we already know the answer to. Square root of 4, square root of 4. Where did that random scribbling come from? That's weird. Okay, so this would be 4 to the 1/2 times 4 to the 1/2. from what we've seen with exponents before, when things have the same base, what I can do is add their exponents together. So 4 to the 1/2 plus 1/2, which is, well, 1/2 plus a half is a whole, so that's 4 to the first, which is 4. Again. Yep. Kind of fun. Maybe, maybe not. All right, but earlier today we established that when I do the square root of 4 and the square root of 4, I get 2 times 2. So what that tells you is when I'm looking at this 4 to the 1/2, that's the same as 2. Ah, okay. So 4 to the 1/2 is the same as 2, which is the same as the square root of 4. So yes, these two are actually equal. Doing a root is the same thing as being able to do a fractional exponent, which is where this comes from. Interesting? I hope so. Let's do some interaction with these two. So we're going to be using all those rules that I talked about to do some examples. So what we're going to do for this example is we're going to rewrite the fractional exponents as radicals. Rewrite as a radical and simplify. Perfect. So we're going to take something that has a fractional exponent and we're going to change it into something with a radical. So hopefully you look at this and you're like, 1/2. The denominator is a square, which means is a 2, which means it's going to be a square root. So this is the square root of 64, which we've calculated many times before to be 8. Let's do another one. Suppose we have 81 to the 1/4. I love this pen when it works well, and only then. So this would be a 4th root of 81, which hopefully you remember 81 is the same as 3 to the 4th. If not, you could factor it. And then you're like, oh, 4th root of something to the 4th power, that's just going to be a 3. Woot woot. Let's do some more. So here's where usually people have a little bit of struggle bus. So say I've got 16 to the 3/4. I've got some choices. There's 2 ways. Blast it. I could write this. I have the 4th root of 16 to the 3rd, or I could do, I have the 4th root of 16 to the 3rd power. Now I'm going to choose to do it this way. You absolutely can do it this way, but notice the first thing you're going to have to do is that 16 to a 3rd, and that's going to be huge. So I'm going to avoid that entirely. So I'm going to start by using this one. So I usually try to pick the one that will give me smaller numbers because that's going to be easier. So I usually try to do the root first. So hopefully you remember that 16 you can write as 2 to the 4th power. If not, you could take 16 divided by 2, divided by 2, divided by 2 to complete its factor tree, and that would give you 2 to the 4th. And then you remember the 4th root of something to the 4th power is totally just going to give you the 2 back. And I haven't dealt with that cube yet, but now I can because I've got something simple inside the parentheses. So 2 cubed is just 2 times 2 times 2, which will give you 8. So I would advocate when you run across ones like that to try doing the root first, because usually it will be a little bit easier. It's not always easier, but usually it is. Okay, let's do our last one. This is probably my favorite one. So say we've got 16x to the 4th y squared to the 1/2. So I've got to use one of my rules of exponents to do this one. So I got to make sure everybody gets a 1/2 power. So I'm going to be distributing here. So I'll get 16 to the 1/2, x to the 4th to the 1/2, right, squared, y squared. There we go. Okay, so hopefully you remember when we do exponent to exponent, that's the same as multiplying. So for the first one, I'm just going to end up with the square root of 16, which is kind of nice because, well, that's all you can do with it. And here I have x to the 4th to the 1/2. When I have power to power, you multiply them, so I end up with 4 times 1/2. Let me just use parentheses there because my times dot isn't showing up very big. And then I have y squared to the 1/2, so you end up multiplying those. That's nice. So I'm going to do some cancellation here. 2 divided in half is just going to be a 1. And then 4 divided in half is just going to be a 2. So when the smoke clears, square root of 16 is going to be 4. X will be to the squared power. And then y will just be to the first power because 2 divided in half is just 1. So that one simplifies real nicely. I like it. I like it a lot. So notice I'm using my exponent rules to do this. So if you forgot your exponent rules, now would be a good time to brush up on them. They were back in chapter 2. Oh no, wait, they were in chapter 1 also. They're in a lot of places. We've been using them a lot. Let's go to the next page. Cool. All right, let's do another rewrite. So this time I'm going to start with something with roots and I'm going to rewrite it with just rational exponents. So this is a little bit of a different example and it's actually simpler than the last one we did. Rewrite, because I'm not going to have to simplify, I just have to rewrite with rational exponents. Perfect. All right. So for A, we're going to do the square roots of 5. And that's just going to be, since it's a square root, my denominator of my fraction will be 2. So this will just be x to the 1/2. And then let's do the third root of 30x. So everything's being rooted by the cube root, so everything needs that 1/3 power. So you could write this as 30x to the 1/3. Or you can distribute that power, and it really doesn't matter. You can do either or. You can do 30 to the 1/3 x to the 1/3 so that they both get their... That does not look like a 3. Come on, undo. There we go. That's better. Sorry. Since they both get that 1/3 power, let's do another one. Let's say we have the fourth root of 2 over 3. Ooh. So this is the same as 2 over 3 all to the 1/4 power, since my power of my root is a 4, and that's going to be the same as 2 to the 1/4. Didn't stop there. Over 3 to the 1/4. Writing bigger has some advantages here, so you can easily see your 4s. Let's do one more, just so we're all on the same page. I think you guys will get this part pretty easily. It's not too bad. So let's say I have the 6th root of 3x y to the 5th. So this is a little more complicated example. I'm going to do another one like it actually now that I look at this one. Definitely going to do an e. So everybody gets the 1/6 power. I'm going to make a mental note that y is to the first power here, and, or sorry, y is to the 5th power and x is to the first power. 1/6, and then I'm going to grab my pink. I'm going to distribute this along. So remember, I'm going to be multiplying my exponents. So I'll have 3 to the 1/6, x to the first to the 1/6, and then y to the 5th to the 1/6. That's a 2. Why did I start writing a 2? I don't know. So remember, we're going to multiply these exponents together, as we've already seen. So I'll have 3 to the 1/6, x to the 1/6 times 1, which is 1/6, and then y to the 5th times 1/6, which will be 5/6. Hopefully that went okay for you. Let's do one more just to check. So that one was a little harder, as we do. What I would suggest at this point is I'm going to write a new one here. Oh, no, it's not picking up my pen. Come on. Oh, I wanted green. Eee! And what I want you to do is pause the video as we go and ask yourself, what fractional powers do you think each of these pieces would have? Okay, so pause, see what you get, and then unpause to get the answer. Got it? Okay, you should be unpaused. So this is going to be everything to the 1/4 power. And then I'm going to go ahead and distribute my 1/4 in. So I'll have 5 to the 1/4 x squared to the 1/4, and then y cubed to the 1/4. And then I'm going to multiply those exponents. So 5 to the 1/4 isn't going to change. It's got nothing to multiply. It looks like I'm writing 5 to a plus sign. I don't know why it wants to not pick up the fourths. X is going to be 2 times 1/4. Use some parentheses there. And y is going to be 3 times 1/4. Let's make some more space here. It took up way more space than I thought it was going to. Cool. And then I'm going to do my multiplication. So still have 5 to the 1/4. Can't drop that guy. He's hanging out, doing his thing. Let's write a better 4 for him, though. We owe him after the terrible 4 I gave him last time. So line, and then that's better. Okay. So 2 times 1/4 will give me 2/4. Remember, you multiply numerators, multiply denominators, and then y to the 3/4. Now I can reduce the fraction for x since this is an even power. 2/4 is the same as 1/2, so I'm going to go ahead and do that. Please don't forget to reduce fractions. Or if when you write your answers and you go to check them, you're like, oh, well, my fraction's slightly different, and you notice that it's just the reduced fraction version. Hey, those really are the same. It's okay. You just forgot to reduce. That's all. It's okay. Whew. Let's do some more examples. So I'm going to do one last type of example of how to manipulate these between the two. Actually, I think I'm going to get a new page because I'm taking up too much space with this one. All right, last type of example. So we're going to use the properties of rational exponents to simplify each of these. So it's going to be a little bit more involved, but I believe in us. Use the properties of rational exponents. So all those properties and rules I did earlier. To simplify each expression. Alrighty, here we go. So I got 4 to the 1/4 times 4 to the 1/4. I actually really like this one, so I hope you will too. So notice I've got two things with the same base, so that means I can combine their exponents by adding since they're multiplied by each other. So I have 4 to the 1/4 times 4 to the 1/4, so I can add their exponents. So 1/4 plus 1/4. Which is really 2/4, which reduces to 1/2. And then you're like, ooh, 1/2 power. Isn't that just a square root? I agree, it is just a square root. So this is really the square root of 4, which we know to be 2. Trippy? I hope so. That one simplifies so nicely. So one thing to note about this is sometimes moving into radical notation makes it easier to recognize the roots you can use. The roots that root. Do. So I got 8 to the 1/3 for my next example. And then cubed. We're going to use our properties to fix this up. So hopefully remember things from powers to powers means I can multiply their powers. So I should have 1/3 times 3. Remember with fractions, we think of this one as being over 1, so we'll multiply numerators, multiply denominators. I don't like those lines I've drawn. So this is going to be 8 to the 1/3 times 3, which is the same as going to be 3 over 3, if you like, which is really 1 because everything divided by itself is 1. So this is just 8. Did you see that one coming? I hope so. So this is a little bit of what we usually will call like symbolic tomfoolery. I've just got to move my symbols around so I can combine stuff and get things to simplify. I'm making new things for mold creation. It's a beautiful thing. Okay, let's try another one. Yeah, let's do this one. So say I have x to the 4th times y cubed, and that's all being multiplied by x to the 3/4 and y to the 2/3. Woohoo! So hopefully one of the things you remember about multiplication is that 2 times 3 is the same as 3 times 2, and this multiplication means I can rearrange this in any order that I want. So I'm going to put all my x's next to each other. So I'll have x to the 4th times x to the 3/4, and then my y's next to each other. So I have y cubed times y to the 2/3. And then you remember earlier, like we saw in A, that if they have the same base, then I can add together their exponents. So for x, I'm going to get x to the 4th plus 3/4. Nope, that 4 is terrible. Good times. And for y, I'm going to have y to the cubed plus 2/3. So now I need to find common denominators for this. And so the denominator for 4 and 3 are just going to be a 1. So clearly my common denominator for the x's is just going to be 4. So I'm going to have to multiply by 4 over 4. And then for y, I'm going to have to multiply by 3 over 3. You really didn't expect having to do this in an exponent, did you? Maybe. I don't know. Depends on what kind of day you're having, I guess. So let me rewrite this because it looks like a mess. Mess! Just make your x kind of big, so then you have more space. So 4 times 4 will give you 16 over, and then 1 times 4 will give you 4. That was supposed to be a 4. It looks like an x. Plus 3/4. So again, just doing a common denominator. Times, because they totally can see that. 3 times 3 will give me a 9/3 plus 2/3. So finding common denominators so I can add. So x is going to be, no, I don't want the keyboard, thank you. That was weird. So you add together your numerators, 16 plus 3 will totally give you 19/4, because we saw that one coming, right? Beautimus. And then y, 9 plus 2 gives me an 11/3. That's just the funnest thing we've ever done. That was a mess. I hate it. Thanks, I hate it. Yep. Oh, me in a room by myself talking to myself. Just as weird as being in class. Whee! Come on. Recognize my pencil, please. There she goes. Okay. Last but not leastly, we have our final example. 27 a to the 6th, b to the 3rd, all to the 2/3 power. I believe in us. This one's going to be a little challenging, but I think we got the muscle to do this. So the first things first, I'm going to distribute my exponent across all of my factors. So 27 is going to get a 2/3. A to the 6th is going to get a 2/3. B to the 3rd is going to get a 2/3. Look at that. It's magical. I'm going to give myself some more space. This was not a part of this problem, but yet somehow ended up near it. Whoops. My lines is a little off. Okay, so 27 to the 2/3. I'm going to rewrite this with the radical notation. So I'm going to do the cube root of 27 and then square it, which is something I did earlier. Like when I ran into these fractional powers, I thought, oh, it's going to be easier with a number if I do the root first and possibly make it smaller and then square it. And usually that'll work, sometimes it won't, so just be aware of that. Okay. And then for these, since I have power to power, I'm going to be multiplying. So I have a to the 6th times 2/3. I think I'm going to use parentheses for this. And then b to the 3rd times 2/3. So I'm using parentheses and then putting my fractions over 1 so I know how to multiply. Hopefully you remember the cube root of 27. I can, well, rewrite 27 as 3 cubed squared. And then for a, I'll do 6 times 2, which will give me 12 over 3. And I'll divide those out in a minute. And then b, 3 times 2 will give me a 6 in the numerator, and 3 times 1 in the denominator will give me a 3 also. Looking good. Keep going. I believe in us. The cube root of 3 cubed, those are all going to, that's way too many 3's. So if we remember that according to our rules from last time, that's just going to give me a 3 and it'll be squared. And then a, 12 divided by 3 is just a 4. B, 6 divided by 3 is just a 2. And then last but not leastly, I'm going to square this 3 and get 9. A to the 4th, b squared. Doesn't that one come out pretty? It's so nice. I love it. Okay. Last but not leastly, let's do some rewriting to get rid of negative exponents. So we had that rule for negatives. If I have something to a negative exponent, I can just do 1 over it instead. Woohoo! So we're going to be using that in these examples. So we're going to rewrite each expression as a positive exponent. So be mindful of the fact that I'm going to make everything be positive, not just some of them. Okay. Why? Why does it always screw up the first thing I write? Let's do 8 to the negative 1/3. I've used 8 a lot, but hopefully you're familiar with them. So the first thing I'm going to handle is the fact that it's a negative exponent by rewriting it so that it's in the denominator, and therefore it becomes positive. And then I'm going to rewrite it as a radical, because this will be the cube root of 8, which we've done many times and seen that it's just 2. Good times in math land? I hope so. Let's do 16 to the negative 3/4. Just when you thought it was safe, I gave you a fraction that didn't have 1 as the numerator. Woohoo! Okay, so once again, first move, always make it positive because it's nice to be positive. Just kidding. It just usually makes it easier to deal with. So I'm going to rewrite this using radical notation. So I'm going to do the 4th root of 16 and then cube it. So then we're going to handle the 4th root since it's inside the parentheses. The 4th root of 16 is 2. And then when we cube it, we will get 8. I must have been in love with 8 when I was writing this lesson because, man, there's a lot of 8 showing up. So I just lost my whole document. Welcome back. I accidentally closed it, so this is not E that we are on. Boy, does that really mess with the flow of things. It didn't even ask me if I wanted to save it. It just closed it and called it good. That's the weirdest thing I've ever had happen. Having all kinds of technical issues today. Hope y'all are doing well. Let's do 27 to the negative 2/3. There's no way for me to back up and see where I left off either because I'm in the middle of recording. Should be interesting to watch this back and try to edit it. So let's see. Let's handle that negative exponent first. Make it positive. 2/3. Okay, and now I'm going to rewrite it in radical notation. So I'm going to be doing the cube root of 27 squared. Hopefully you've seen me do the cube root of 27 enough times to know that that's just going to be a 3. And then when we square it, we're going to be squaring 3, and that'll give me a 9. Beautimus. Let's do our last example of the day and hope that nothing in our computer crashes between now and then. It's not her fault. Well, actually I named it a guy's name, but don't worry about that. She's like 6 years old, and I'm asking her to do a lot of things today. 81 x to the 8th to the negative 3/4. This one's going to be an adventure, but I believe in us. We've done harder things. So first things up, we're going to rewrite this as a positive. So 81 x to the 8th to the 3/4. Then let's go ahead and distribute our exponent in. So just make your fraction big enough to where you've got room to move. So I'll have 81 to the 3/4 times x to the 8 to the 3/4 power. That 4 just doesn't want to look like a 4, and neither does this one. Get your act together, 4s. I see you. Okay, so just like you've seen me do a million times when I encounter a number, I'm going to rewrite it as a radical. So 4th root of 81 cubed, and I'll handle that in a minute. And then for x, we're going to multiply because we've got power to a power. So I'm going to have 8 times, so I'm going to use parentheses because that dot doesn't show up very good, 3/4. So as you look at this, be careful. I'm going to be thinking of that 8 is over 1. Remember, if I'm going too fast, you can pause, rewatch, slow it down. If you open this in YouTube, you can watch it in half time or double time. I should have said that earlier. Too late now. 4th root of 81, hopefully you know that 81 is 9 squared, or you can think of it as 3 to the 4th power. So since it's 3 to the 4th, the 4th root of it is just 3. So I've got 3 cubed here. And then for x, I'm going to go ahead and do some reduction. 8 divided by 4 is 2. So I end up with 2 times 3, which is 6. So, and then we cube 3, so 3 times 3 times 3, which totally gives me 27. X to the 6th. Voila, as they say. Or voici, which is, and here it is. Because voila is, and there it is. One of those is right. I haven't taken French in 8 years. Why am I trying? I don't know. Okay, remember, you can rewatch, you can pause, you can go back, you can go forward, you can re-look at the examples. I'm also going to post a bunch of extra examples like I did last week, so make sure you watch some of those if you're feeling uncomfortable. And you'll have a quiz over 7-1 that goes along with this. Good luck. I'm here for you. Please don't be afraid to email me if you have questions.